Good morning, everyone. Today I'm excited to present this work on 4D-STEM nanoscale strain analysis in van der Waals material, advanced beyond planar configuration, in which use advanced 4D-STEM image combined with machine learning technique specifically focus on excite wave power Kapstrom method. 2D van der Waals materials have captured tremendous attention because of their unique optical, electronic, or mechanical properties. However, these properties are not static. They are strongly influenced by local strain field within the material, strain atomic spacing and lattice symmetry, leading to changes in band structure, optical transition, and even mechanical strength. Therefore, understanding the accurately mapping these local strain fields is critical to this work aimed to tailor material property for real-world application in electronics and photonics. To study this nanoscale structure, transmission electron microscopy, or TEM, has traditionally been used. However, in extremely thin material like 2D layer TEM face challenges. Because the materials are so thin, the signal-to-noise ratio becomes low, making it difficult to extract detailed information about strain at the nanoscale. This leads us to more powerful method, four-dimensional scanning transmission electron microscopy, or 4D-STEM. 4D-STEM work by scanning a focused electron probe across the specimen, regarding a diffraction pattern at each pixel. This produced an incredibly rich dataset, allowing us to extract information about local crystallography, strain, and rotation across the wide area, without sacrificing spatial resolution. However, even 4D-STEM has its limit. Mapping strain in complex structure like twisted bilayered or nanohedral structure is difficult because their small size and irregular geometry complicates analysis. To address these challenges, this work incorporates machine learning technique into a workflow. Specifically, this work used deep learning-based approach to assist in identifying and analyzing strain pattern automatically and accurately. One crucial innovation in this work introduced is the excite wave power Kapstrom. The EWPC enhanced the analysis of 4D-STEM data by isolating key diffraction information, allow for automated, accurate, and scalable strain map across the complex nanostructure. This work tested method on two representative structure. The first is 2D molybdisulfide thin film. The second is one-dimensional moly oxide nanorock coated with molybdisulfide layer. These examples allow this work to demonstrate the method robustness across different materials types and geometries. Moreover, the approach is not limited to van der Waals material. It can be generalized to other low-dimensional nanostructure as well. Now, an important aspect for strain measurement is obtaining precise lattice parameter. Traditional diffraction methods tend to average over large area, which washes out fine strain details. Instead, this work used converged beam electron diffraction under nanobeam electron diffraction conditions. Here, a small electron probe created using a small condenser aperture illuminates the sample and produces highly localized diffraction pattern. And this pattern, particularly to zero-order Laue zone reflections, are extremely sensitive to small lattice distortions. In this technique, the EWPC extracts the key lattice information from the nanobeam electron diffraction pattern. This intensity, recorded on the pixelated detector, corresponds to the electron wave's power spectrum, which carries information about interatomic spacing. By applying capsular analysis, the EWPC highlights the sharp peak representing specific lattice distance, even in noisy database. This allowed us to distinct tiny lattice parameter variation, essential for accurate strain measurement. The strain mapping process itself involves a four-step workflow. The first is peak identification. Peaks in the EWPC are detected using a difference of Gaussian method. This filters noise and enhances real lattice signal. Second is point cloud generation. The identified peaks are compiled into a weighted point cloud representing local atomic spacing data. And third one is clustering. K-means clustering is used to group peak into distinct cluster corresponding to atomic arrangement or material domains. And the fourth one is strain measurement. The local strain is evaluated by comparing measurement peak position to those in a reference unstrained area. The technical innovation here is achieving subpixel accuracy in peak location. Initially, the difference of Gaussian method gives peak positions to the nearest pixel. To refine this work applied a small circular mask, the radius which is 2 pixels, around each detected peak and compute the center of mass of the intensities. The method greatly enhanced the precision, crucial for a high fidelity strain and rotation maps. This work also optimized computational efficiency using desk array for parallel processing rather than the NumPy array that is broadly used. And these speed up the analysis across large datasets without compromising accuracy. Moreover, to minimize computation, this work only needs to track 2 non-parallel peaks per position, greatly reduce the complexity without losing essential strain information. Once the peaks are tracked, 2 deformation metrics are calculated. First one is d-car, based on the Cartesian coordinates, and second one, which is d-vect, which is based on selective vector displacement. Both metrics allow extraction of rotation and strain fields simultaneously. Strain maps reveal area under tensile or compressive stress in specific direction, while rotation maps capture local angular distortion relative to reference. In this molybdisulfide thin film, this maps clearly visualize localized stress region and the clockwise rotation relative to unstressed area. Regarding precision, the strain map's accuracy is estimated at around 1.1%, and the rotation map's accuracy is about 4.47 degrees. Moreover, this work observed that large distance between peaks improved the strain measurements accuracy, an important consideration for future work. One particularly exciting capability of this method is its application to twisted multi-layer structure and moire pattern. When 2 layers of 2D material are slightly rotated relative to each other, moire pattern form, producing distinctive peak in the EWPC. This method can separately track the strain and rotation of each layer, something conventional method often cannot do. This opens possibilities for analyzing interlayer interactions, stacking faults, and twist angle dependent phenomena in layered materials. In the moly oxide and molybdisulfide heterostructure case, despite the low image contrast, EWPC combined with difference of Gaussian filtering successfully isolated distinct peak clusters for each material. The resulting strain map shows that the moly oxide nanorod experienced tensile stress, while the molybdisulfide shell primarily underwent rigid body rotation. This detailed multi-material mapping would have been extremely challenging using traditional method. In conclusion, this work shows that combining 4D-STEM image, machine learning, and EWPC method allow for precise, detailed, and scalable strain mapping in complex nanostructure. This enables new understanding and control of material properties, paving the way for better electronic, photonic, and quantum device based on 2D materials. And finally, to make this powerful technique accessible to the broader community, this work developed a software tool called Strain Mapper. Strain Mapper includes example datasets, automated peak detection, clustering modules, and customizable strain analysis pipeline. And if you're interested, feel free to check it out. And this is my presentation. Thank you for your attention and your time. Hope you can have a good day.